Welcome back to section 6.6, exponential and logarithmic equations. Today we're going to be wrapping up chapter 6, so it's really important as we finish up today that you go back and watch some of the videos from chapter 6 or practice some of the exercises as we prepare for our chapter 6 text coming up. All right, let's get started. Today we are going to be wrapping up everything about exponents and logs and how to solve equations with them in them. So the first and easiest probably property to apply is this one-to-one property of exponents, which says if your bases match, then you can set the exponents equal to one another. So let's jump right in. So here we have matching base. So let's jump right in. So here we have matching bases, and instead of just crossing them out, which is what you could do, we're going to show you the tools you need to cancel them out. So instead of just crossing it out, what I'm going to do is the way that we eliminate a base is what we logarithm it with the same base in a log. So log base 5 of 5 to the 2x is equal to, and what you do to one side you have to do to the other side, log base 5 of 5 to the 3x plus 2. And this is just going to help us be prepared for when we get into slightly more difficult ones. Those 5s are going to take each other out, and we'll be left with 2x on one side. Same thing over here, equals 3x plus 2, and then we can solve from there. So draw a line like we've been doing, move the 2x over, and you'd minus 2x minus 2x, 0 equals x plus 2. Move the 2 over, and you'll get x equals negative 2. If you want to plug that back in to check, you can, and find that when you plug it back in, you probably get 5 to the negative 4 equals, if you plug in negative 2 here, you get negative 6. Minus 2 is 5 to the negative 4, so it checks out. All right, let's keep going and do another one. This one's going to have one extra step in it, and you'll notice the bases aren't exactly the same, but they're pretty close. And so I'm going to rewrite 5 to the 2x, and I'm going to find a way to write 25 so it has a matching base. So another way to write 25 such that it has a matching base would be 5 squared. All I've done is replace the 25 with the 5 squared and left everything else the same. And now if we want to get rid of some stuff, we could start using the logs and say log base 5 again to take it out and leave us with 2x. And on this side, if we log base 5 it, we'll apply one property before we continue. So log base 5 of the whole thing. And we can use the product property or the power rule to take this 3x plus 2 and move it to the front. And so we'd be left with 3x plus 2 log 5 of 5 to the 2. We know that log 5 and 5 will take each other out, and we'll be left with 2x equals 2 times 3x plus 2. If you recognized earlier that you could have used the exponent power rule and combined them in that step, you're more than welcome to. It's the same rule working itself out in the logarithm and the exponent. So we'll finish by distributing and solving. 2x equals 6x plus 4, which means that 4x is equal to, if we move the 2 over, move the 4 over, negative 4, and x is equal to negative 1. So in this one, x equals negative 1. One more time. We'll keep using the 5, it looks like. So we've got 5x equals, and a way to rewrite a square root. Remember, it's really important to remember how to write square roots as exponents. Put parentheses around the 5 and raise it to the 1/2. If we apply the properties of logs, we're going to log 5 it to be left with x, and then we'll log 5 this side as well to be left with x equals 1/2. All right, we'll keep going. We'll see what happens when we get a little trickier. There's no number that's going to get us 100, which is why I think it's really important to learn how to do this with the logs. Take the log base 2 of 2x equals the log base 2 of negative 100. So what that's going to do is that's going to show us a little bit quicker what we're going to get for our x value. We've got an x by itself, and we look right here and we say, we learned about domains of logs in the last section, and we learned that the log cannot have a negative inside of it. So that is a bad number or an error or a domain restriction. So x, there's no number that could equal x. So x equals undefined. Does not equal more, x is undefined. Or you could say no solution. All right, let's keep going and see if they have what we have next. All right, sometimes they give you a different base. We need to learn how to solve things with a different base, which is a little tougher. We're going to use the normal rules to solve. It says one of the terms has a base 10. You use the common logarithm. And if none of the terms have base 10, use the natural logarithm, though you could solve it with either. They're just offering the natural logarithm as a normal solution for these problems. So because there's not a base 10 here, we're going to use the natural log. So we're going to ln both sides. And then we're going to apply that power rule one more time to take all of those powers and bring them out to the front. So we're going to be left with x times the ln of 2 equals x plus 1 times the ln of 3. And it's important to think about ln of 2 and ln of 3 as just numbers. They're hard numbers that we don't know the answer to. They're going to be long, long decimals, but they're just numbers, and we can treat them as numbers. We can distribute them like numbers, divide them, multiply them. We can treat the whole function of natural log of 2 like a number. And so that's what we're going to do. We're going to treat ln of 3 just like we would a number and distribute it. And so we've got x times ln of 2 equals x times ln of 3 plus 1 times ln of 3, which is just the ln of 3. And now we're going to try to get those x's by themselves. So we're going to combine like terms, move them over to the same side. So we'll get x ln of 2. We'll subtract that over. So we got minus x ln of 3 equals the natural log of 3. Now how do we turn two variables into one variable? We factor it out, or divide it out, reverse distributing it from the parentheses. And we'll get an x on the outside. And we're left with ln of 2 minus ln of 3, which is just a number. It's an ugly number, but it's just a number. And so the final step we'll do before we get x by itself is we'll divide out that whole term, ln of 2 minus ln of 3. And what you do to one side, you have to do to the other side, ln of 2 minus ln of 3. And we'll be left with an x term that we did not need a calculator to solve. X equals, all of that cancels each other, ln of 3 divided by ln of 2 minus ln of 3. All right, let's keep going. Now we're going to learn how to solve equations containing an e. It's going to be a little more specific and sometimes involve a decimal or sometimes involve just leaving it alone. I know on the My Open Math homeworks, you can leave them alone. You can just type them in as the full logarithmic expression and you'll get full credit. It's an important thing to remember as we go on. So first thing we're going to do is treat this like a normal problem. I'm going to divide by 3 on both sides because there's a 3 on the outside, just like we would if it were an x squared or an x to the 4th or anything. We'll be left with e to the 0.5t equals, parentheses this up so it's a little easier to treat, 11 over 3. Now the same way we got rid of a base before is the way we're going to get rid of an e, but the property that we have to remember is that the natural log of x is just the log of x with the base of e pre-built into it. So the way we get rid of the e is we natural log the whole side. And what you do to one side, you have to do to the other. And so that'll take care of that, just like it has been doing. We'll be left with 0.5t equals ln of 11 over 3. And how do we get rid of a 0.5? We multiply by 2. 2 times 0.5 is 1. What you do to one side, you have to do the other side. So we'll multiply this side, and we'll be left with t equals 2 times the natural log of 11 over 3. Box it and be done. It's okay to not evaluate that natural log. If you want to type it in a calculator and get 4 or 5 decimals, you can, but it is perfectly okay to leave it alone. Say, I know how to do the math, I know how to do the algebra behind it, and if I needed to type it in a calculator, that's the simplest form to type it in. I'll do this one more time. We're going to combine like terms first, just like we would with any variable set. So let's get the e's on the same side. So 3, draw our line. How do we get those e's on the same side? We're going to subtract them. Minus e to the 2t, minus e to the 2t. You'll see something really nice happen. Since it has the same variable, same exponent, same everything except for coefficient, we're going to be able to combine those two and be left with 3 equals 6 e to the 2t. Saying if you have 6 desks and I take away 1 desk, you have 5 desks. If you have 7 t-shirts and I take away 1 t-shirt, you have 6 t-shirts. If you have 7 e to the 2 t's and I take away 1 e to the 2t, you have 6 e to the 2 t's. Now we're going to keep going with our algebra. Divide by 6, divide by 6. Be left with 1 over 2 equals e to the 2t. Remember, how do we get rid of that e? If it's got a base of e, we natural log both sides. That'll cancel it out on the right side. What you do to one side, you have to do to the other. And we're left with 2t is equal to the ln of 1/2. One last step, divide by that 2 to get t by itself. T equals the natural log of 1/2 divided by 2. Awesome. So we've been solving some logarithmic equations and solving some exponential equations. Now we're going to get to one that's a little bit trickier just because of the format. This one's going to involve a little bit of u substitution that we learned about back in the quadratic section and recognizing two e values as similar but with different exponents. So the first thing we're going to do is get them all onto one side before we think about this u sub. So I'm going to move everything over to one side. So I'm going to be left with 0 on this side, and I'll have e to the 2x minus ex minus 2. Now this is a little bit more difficult to recognize. And I've been doing it a long time, so it's easy to see, but that doesn't mean that it's easy right away for you to see. So it's really important to focus in and look at what does this kind of look like. It kind of looks like quadratic equations that we've solved forever. We just need to do one step to make it really look like them. And that step is to recognize that if you have multiplied powers, you can unuse a property and you can make them exponents of each other. You can take those exponential properties and use one in reverse. Use the power exponential property in reverse to write this as e to the x squared. That comes from that property that says if you have a base raised to the a raised to the b, it's the exact same thing as the base, well, let's not use b. Base raised to the x raised to the y, it's the exact same thing as b to the xy. Well, all we did is undid that power. And what that power is going to help us do, I can leave that there, it's going to help us recognize this as a quadratic. Minus e to the x minus 2 equals 0. Now, wouldn't it be really nice if that wasn't e to the x? Wouldn't it be really nice if that e to the x was something like a variable, like u? So off to the side, I'm going to make a note that u equals e to the x. And we're going to substitute that, or u substitute that in. So u squared minus u minus 2 equals 0. And that looks like a nice, neat factor. The 2 breaks into terms, let's see, probably -2 and +1. And so we can factor that nice and neat. U minus 2, u plus 1 equals 0, which means we've got factors and zeros. U equals 2, u equals -1. But remember, u was never in our original problem, so once we get to our final answers, we need to go and back sub in that original u, sub u back in. And so instead of u equals 2, we're going to have e to the x equals 2. And instead of u equals -1, we're going to have e to the x equals -1. And now how do we get rid of that e? It's the same steps we've been doing. We natural log both sides. So we're left with x on this side equals the natural log of 2. We'll do it one more time. Natural log both sides. X on this side equals the natural log of -1. And we've got two answers, but we need to be careful. That's a perfectly fine answer. And this answer over here has a big problem. You cannot have the natural log or the regular log of a negative number, and so we cancel it out and we don't consider it. We're left with only one answer. Cool. Now we're going to work in reverse. We're going to say, well, how do we get rid of logs? Instead of applying logs to get rid of exponential functions, we're going to apply exponential functions to get rid of logs. And so if we zoom in, we'll see, oh, we've got a function that has a log built in, but we want to get rid of that log. So let's show you how to do it. First thing we're going to do, get the log by itself. You always want to get that log or that exponent by itself before you solve it out. So ln of x is equal to 4. And now how do we get rid of a natural log or any exponential or logarithmic function? Is we do the opposite. So the opposite of the natural log before was basing it with e. And so that's exactly what we're going to do. We're going to base the whole side with e, or exponentiate it by a base of e. But what you do to one side, you have to do to the other. So we're going to exponentiate the other side with the base of e. That will take care of our natural logarithm, and we'll be left with x equals e to the 4. Which is just, e is just Euler's constant. It's a constant that is 2.71 something something something. If I type in second e to the 1, I get 2.71828. It's a constant that's on your calculator and pre-built in, and it is okay to leave it as e. Let's do it one more time. We're going to have a very similar problem where we need to get that natural log by itself. So we're going to divide by 2, divide by 2. end up with a natural log of x plus 1 equals 5. Exponentiate both sides. Remember, the opposite of a natural log is e. What you do to one side, you have to do to the other. So we've got x plus 1 equals e to the 5. Can't leave x not by itself, so we're going to subtract 1, and we'll be left with x equals e to the 5th power minus 1. Awesome. So we've talked about the opposite of a log is exponentiating it. The opposite of an exponential is logging it with the same base. Both times you have to use the same base. So you need to think about what is the base of this log I'm working with, and how do I apply the opposite function to it, or the inverse function to it. We've got the exact same property happening with logs, though if you can exponentiate with the correct base, you don't need to worry about memorizing the one-to-one property, though it's still good to know. If you have the same base on a log, then your inside arguments have to be exactly the same. So for instance, how do we get rid of those natural logs? We exponentiate with an e as a base, e, so it goes away, and we're left with x squared equals positive 1. And so how do we get rid of a square root? We square it, but remember we introduced the square root, so x is equal to plus or minus 1. And now we should be careful. We need to check and see if there's any extraneous solutions. We need to check and see if those both work because we introduced the square root. Anytime we introduce a square root, we have to check our work because we resulted in 2 solutions and we need them both to work. So if we plug 1 back in, we get the natural log of 1 squared equals the natural log of 1. That works out. And if we plug negative 1 back in, we get negative 1 squared, which is just 1, equals the natural log of 1. Let's do one more step just to make sure it worked. The natural log of what's negative 1 squared? It's just 1, and the ln of 1 does indeed equal the ln of 1. So they both worked, so they're both solutions. So our 2 solutions are x equals negative 1 and x equals 1. And we'll write them both because they both worked. All right, let's keep going. There's one more practical problem, and then we'll wrap it up for this section and this chapter. This practical problem says, using the following formula for half-lives, determine how long it will take before a 20% 1,000 gram sample has decayed. And so we have our principal from back in the day. Even though it doesn't say principal, it's the initial amount. So it's very similar to that aspect of principal from when you were working with the bank and you were compounding interest. We've got the half-life of the substance. We've got time that's passed. And we've got the amount of substance at the very end, how much is present. So this is really just going to be a plug and chug, where A of t is the amount, and they've given us everything else. So did they give us the starting amount? They said 1,000 gram sample. So we got a starting amount. Did they give us, they told us 1/2 already, because we're looking for the half-life. They asked us how long will it take, so that's going to be our variable. Our variable is going to be t because of this how long will it take. So that means t is the variable. So we'll leave t alone. And then we need that capital T, which t is the half-life of the substance. And from our textbook, we have the half-life of uranium. So I'm going to pull that in from the textbooks where it says the half-life of uranium 235 is 703,800,000. So it takes a really long time for uranium to decay to half of its size. So we're going to use that as the capital T there at the bottom, because that's the half-life of the substance. Again, this came from the textbook in the section we're working with. It's just a practice problem, and they give us a whole table of half-lives in our textbook, just in case you need them for an exercise in the back of the book. So we've got ourselves a formula, and we have 2 variables. So a question we need to ask ourselves is, how much do we want left? Well, the problem gave us that. It said we want to watch 20% to decay. How long will it take before 20% has decayed? And if 20% of 1,000 grams has decayed, how many grams are left? This is a percentage problem from back in the day. If you want 20% of 1,000, you multiply 0.20 by 1,000, and you get 200. That's how much is decayed. So you get 200 decayed. If 20% has decayed, 200 has gone away. So you take 1,000 and you subtract that 200 because that's how much has gone away, and you should be left with 800. So instead of A of t, our final answer is going to be 800 is equal to 1,000 times 1/2 t over this long half-life, 703 million 800,000. And even though there's really big ugly numbers, the solve is exactly the same as we've been doing. First thing we need to do is take care of any coefficients or multiplications out front. So we're going to divide by that 1,000. Remember, we can't divide by this 1/2 because it's attached to an exponent. And you have to take care of exponents before you do any division or multiplication because it's attached to a variable, it stays there, and we have to log it out. So we move that 1,000 over. 2 of the zeros go away, and we're left with 8 over 10, which we could definitely reduce to divide by 2. You get 4 over 5 equals 1 over 2 raised to the t to the 703,800,000. And now how do we get rid of a base? The way we get rid of a base, move that over a little bit, is the exact same way we've been getting rid of bases this whole time. We log it with the same base. So we're going to go log with a base of 1/2 of the whole thing. It's going to take out that base and leave us with just our argument up top. But what we do to one side, we have to do to the other. So log with the base of 1/2 of 4 over 5. And so we've got log base of 1/2 of this ugly fraction equals t over 703,800,000. We're getting real practical, but we're able to do it without a calculator so far. Last thing we need to get t by itself is just to multiply that long term over. So we're going to multiply by 703,800,000, cancel them out, and we'll be left with t equals the log with a base of 1/2 of 4 over 5 multiplied by, so I'll put that out front, multiplied by 703,800,000 times the log. Now before we wrap up for the day, I want to do a quick practice with the change of base formula because we've got a not common log and we want to move it to the common log. And if you remember from last section, you take the top and you move it to the top, you take the base and you move it to the bottom. So instead, in order to be able to type this in a calculator, we're going to write t equals 703,800,000 times, remember there's a log on the top and a log on the bottom, and the one that's a little bit above goes to the top and the one that's a little bit below goes to the bottom. So you got 4 over 5 and 1/2. And we've changed our base in order to be able to type it in a calculator and have a nice pretty answer that will work. Particularly if you're using your iPhone calculator or something like that to solve problems like this, you don't have a changeable base. You only have 2 options. You have the natural logarithm, which is base e, and the common logarithm, which is base 10, and neither of those would have solved that, and so that change of base was pretty important there at the end. I'll make that note. That came from the change of base formula. All right, thank you for watching so far. That concludes Chapter 6. If you need to go back and watch any videos or practice any exercises, I think that that's a really good idea to do as you approach your Chapter 6 test this week. And then we'll move on to Chapter 7, remembering there's no Chapter 7 test at the end of Chapter 7, but there is a final exam at the end of this class. Thank you for watching, and I'll see you next time.